and then start sharing the screen so that we are ready. So I believe you should be looking at my iPad screen now. And today, the plan for today is, let's write it down. So CGEng 200. Today is January 13th, 2021. And what we are going to do today, we'll continue a little bit with the introduction. Only one point I want to go over. Then we'll review. I'm sure many of you, if not all of you, have been exposed to the set theory before. And then, as time allows, we will start probably the first new topic to you, which is the counting techniques, which is a way of counting how many outcomes we have in an experiment. Okay. So let's start. Let's start for the first part, the intro. Continuing from what we did last time, I just want to mention slightly about what we call the methods for collecting data. Methods for collecting data. So we can talk about 3 different methods for how to collect data. And why do we need to collect data? Anything, any study we want to do, any enhancement of an existing process or plant or any idea we want to implement, we have to start with some data collection. So where do we get our data from? There are many ways. First way, and I assume you, oh, you don't hear me? Oh.
We can hear you, Doctor.
Yeah, we can hear you, Doctor.
Oh, you can. Okay. Okay. There was big silence, so I thought it's something I felt like, sometimes you feel stupid talking to yourself. Anyhow, so the first method for collecting data is what we call the retrospective or historical data. So in this type of studies, which we call retrospective studies or retrospective data collection, we go to historical data that already exists somewhere. You go to, if you are a consultant, you are hired by a certain whatever company. They want to increase their production, so you ask for the production of the past few months and the cost and everything. So you collect your data from their laboratory. They should have it somewhere. Can you please mute your phone, all of you? Brahim, I think this voice coming from you. Okay. So you go and find the data from history, and this is very popular in the medical field. In the medical field, people always rely on historical data, especially if they want if they come up with a theory that to link something to for example, to cancer or to death, and they go and look into the medical records and see which group of patients had, for example, high blood pressure, those who died of cancer, for example. And the problem with this kind of studies is the cleaning the data usually. Is a challenge, especially medical data, because they record many aspects of patients, and you need to, and usually all of this data is stored in one place, even electronically. Now, even though we have electronic data warehouses, still it's very challenging to extract the specific data that you are interested in. So this is a very popular source of data. Historical data from almost in all fields is used. The other way we do or we get our data is from observations. We just go to a functioning process or a functioning factory, and you spend some time collecting data, just observing what's going on. Very popular example of this, for example, when if you report to Rido or to Vodafone that you are getting a weak signal in a certain location, and if this complaint is repeated from multiple people, then what they do, they send someone, and they do what we call the RF survey. They start checking the strength of the signal in the area, and usually they have this car which has a receiver, and then they move around multiple times and observe the data, and then they take it back and they see what they can do. And very popular way to do it, sometimes they just need to, what we call, to tilt the antenna, to reduce the angle of the antenna so that it's facing down more, to increase the strength of the signal for in the weak area. And nowadays people are using drones to do this, because now if you are just checking the signals in your car, you have to stick to the streets, and you cannot check all the points. Now you can stick just a receiver on a drone and can fly almost everywhere, and you'll be able to collect more data. So this is one example of observational data. So you don't rely on history. You go to a working place, and then you just collect your data by observing a functioning process. The last place where you can get your data is by what we call a designed experiment. A designed experiment is whenever either you are designing a new thing, so you do not have anything in place, so you have to do the experiment in the lab, and then you collect your data in the lab, or it's very hard. You want to study, for example, the effect of introducing a change in a certain process for a big factory. You cannot just go and tell the people, for example, in Qatar Gas or QP, that I want to study the effect of increasing the pressure in that boiler, how it will affect the production. It's this is not a simple thing to do. Even their regular maintenance, they plan it months ahead, because it might affect the production, and there are contracts, and it will introduce a lot of disturbance. So you design your experiment in the lab to mimic the real life processes or scenarios or functions. And then in the lab, the beauty of doing things in the lab, you have full control of what you want. You can change all the variables you want to do, and you can get all the data that you are interested in. And sometimes, like doing things in the lab, you play around it. For example, I have a student just 2 weeks ago. He was collecting data in the lab. We want to study the effect of the distance between the transmitter and the receiver on the quality of the signal. So you can do this by just keep increasing the distance between the transmitter and the receiver, or you can collect one set of data between the transmitter and the receiver, and then you play with this data. You start adding noise to this data to simulate in real life that the transmitter and the receiver are getting farther from each other. So it's in the experiment or inside the lab, you can do a lot of things that will enable you to collect all the data that you are interested in, and you can play around it the way you want. So generally, these are the three ways of collecting your data. As I said, the design experiment is not the easiest one, but it will give you the right data that you are interested in, and usually you don't need to play with it a lot. But historical or retrospective data is the hardest one to deal with, because it's not stored in a way that to serve a specific function, but rather it's a general data, and it's your role to identify what type of data you're interested in. The challenge there sometimes is that you don't know what exactly you are looking for, what factors you are looking for, and hence you need to go through all the available data until you reach a point where you find the factors that might affect the study you are doing. Okay, so this is more or less what I wanted to add to the introduction part, and we move to the second part, which is the set theory. But before the set theory, let's do some definitions. And let's define what we call a random experiment. What's a random experiment? Very simply, it's an experiment, right? It's an experiment that results in a different outcome or result, that results in a different output or outcome, even if you repeat it in the same manner. So a random experiment is an experiment that if you repeat it, you'll get a different answer every time. What's not a random experiment? For example, in your room, you turn on the light will come out. This is an experiment. You turn on the switch, unless there is a power disconnectivity or something, but regularly, every time you turn on the switch, you get light. So there's no randomness in this. However, a random experiment is something that when you repeat it, you'll get a different answer. Let's do some examples. So what are some examples of a random experiment? We can have popular examples from probability books, like tossing a coin. If you toss a coin, if you stand in the same location at the same time today, and you put your hand at the exact same certain height, you flip a coin, you might get a head. You repeat it a minute later or the following day exactly at the same time, then you get tail instead of a head, and so on. So you can get a head or a tail. I see some of you wrote in the chat okay, throwing a dice. Yes, throwing a dice. again, if you keep repeating it, and many games are built on this randomness of a die. So you can get either 1 or 2 or 3 or 4 or 5 or 6. So even though you repeat it at exactly the same way. Playing cards also full of randomness. Death, one of you said death. Death, it's not sure if the timing of death is random from our point of view, yes, but it's something that you cannot repeat, right? You cannot repeat death to check if it's random or not. Also, if I have a box with 4 colored balls and you pick one randomly, then you might get, for example, you have red, green, yellow, blue. Every time you repeat it, you will get a different ball. So these are like explanatory examples, but in your real life, we mentioned some random experiment. For example, making a call from your mobile and checking the quality of the signal. If you are in your room, in a certain part of your house, and you make a call at certain hour, and then an hour later, exactly in the same location, in your room or in your house, you make a call, you might get a totally different signal, a weaker signal or a stronger signal. Even though Ooredoo did not change the location of their base station, you are exactly in the same part of your house. Probably the charging of your mobile is exactly the same. But there are some other factors that we do not control. Like we are not controlling because the signal from the base station to your mobile is reflected in all the objects that are between you and the base station. And then there are some moving objects. There are objects that get into the way. Also, it's affected by the number of people who are using the network. Sometimes you will not even get a signal because there is no available channel for you to make your call. So this can be looked at as a random experiment. So this is the first definition, which is a random experiment. Let's do another definition, which is the sample space, which has to do also with random experiments. So what's a sample space? Sample space is basically the set of all possible outcomes of a random experiment. So if you do a random experiment and you collect all possible outcomes and put them in a set, we call that set the sample space. And we denote the sample space as script S. We write it like this, as a script S. So let's do S for all the examples that we did above. So for tossing a coin tossing, what will be the sample space? What will have S? What outcomes? What are the possibilities that you will get?
Head and tails.
Head and tail, right? Yes. So head, tail. Yeah, I see someone asking about the notes. Yes, I always upload the notes. So I will upload the notes as well as the link to the recording of the lecture. I will upload it to blackboard. So S in this case is head and tail, throwing a dice example, dice throwing. S is 1, right, 2, 3, 4, 5, 6. Box example, S can be again red or green or yellow or blue. Making a call is a bit tricky. Let's do it. Let's do a new example. What will be S? How many times? How many times you need to toss a coin for you to get ahead? How many times you need to toss the coin for you to get ahead? Yes?
2.
What are the possibilities? As we said, the sample space, you should count all possibilities. What are the...
It will be every time 50-50, so there is no specific number of times.
So what will be the possibilities? Can you give me some?
50%.
No, I'm talking about how many times you need to flip it. So someone might flip it.
Either one time or
Maybe
billion
from
times.
from one to infinity.
Yes,
Yeah,
exactly.
so someone might get ahead for the first time. So one is a possibility. Another one might need 2 times to flip it to get ahead, 3, 4, 5, and so on. And in theory, you can sit all day flipping and you're getting tail. This is very improbable, very weak event to happen, but still it is, from theoretical point of view, it might happen. You keep, even with a fair coin, I'm not talking about a coin that has 2 tails on both sides. No, fair coin, what we call fair coin, that has a head and tail and does not have equal weights on both sides. So in this case, I have an infinite sample space. It will go all the way, as you mentioned, to infinity, and so on. We can come up with every experiment. You can collect all possible outcomes. Let's do a different. Let's do another example. If you take a boat and move 10 meters inside the sea, and then you measure the depth. What will be your sample space? So I ask each one of you to go to a random location in Qatar. We have a big coast in Qatar, like you have Corniche, Lahore, all places. You take a boat and you go 10 meters inside the sea, and then at that point, you check what's the depth of the sea. Will all of you get the same depth? You don't have a boat, so you don't participate. Someone does not have a boat, so you don't have to participate. Only those with boats, they can participate in this experiment.
Doctor, will we be in the same place or like
No,
random
leaving
places?
from, yeah, random places. Yes, random places.
I think there is a small possibility that we will, some of us will get the same depth, but most likely not.
So give me, like, I know this is, we'll not know the exact sample space, but what can be a possible sample space for this? And I just got a coffee from my neighbor to help me in this lecture. Thank you, Dr. Saud.
At least from like the ground level, deeper than the ground level, until
Yeah, if you move 10
Mariana
meters
Trench.
inside the sea, probably the lowest you will get is 1 meter, yeah, right? If you move like 10. So depth will be, for example, x, such that x is between 1 meter and, I don't know, up to 10 meters, maybe 15 meters, I don't know. So you can get any depth between 1 and 15 meters. For example, this is a possible sample space, right? So you can get any depth between 1 and, it's very unlikely to get 200 meters, 400 meters. can be more or less. This is just an example of a sample space. It can be anywhere between 1 meter and 15, 10, 5 meters. I don't know. I'm not a C person,
Doctor?
so yes.
When you make a sample space, do you have to go with the most common ones, or you have to ignore the
No, you have to count all the possibilities. All the possibilities, even the very small unlikely event or very low probability, you have to count them in the sample space. Sample space should contain all the possible outcomes.
So here the depth can be even, I don't know, but it can be even more than this, right? But you're not taking that into account.
Yes. Yeah. I mean, I'm 20, 25, 30. But in Qatar, the sea does not go that deep in 10 meters. That's what, but this can be instead of 15, maybe 25. I don't know.
But doctor, in this question, we are assuming that the highest thing will be 15 meters, right?
Yeah, the deepest point is 15 meters. And
I think that will rely upon the number of people who will do this experiment, because if you have more people, the possibility of two having the same depth will be more.
No, as we will see later, the possibility that two people will have exactly the same depth is 0. We'll talk about this later. We'll keep this question for like in 3 or 4 weeks. We'll prove that it's 0.
Doctor?
Yes.
So the sample depends on whatever the student thinks. So another student may say 0.5 meters to 10 meters. And another one would say 2 meters.
Yes.
So it totally depends.
So if I ask you this question in exam, there is no one single answer for this. Yes. Because I don't know the answer. But if I ask you about tossing a coin, or that one we know, we all can agree on the sample space. But for this one, no.
Yeah,
but if I ask you in the exam, what's the sample space for the temperature in Doha in the summer or in July? You tell me, the possible answer is whatever, 32, 33 to 48, 49, 50. I don't expect someone to tell me it's 10 or 5. That I will not accept that answer, right? So there are some reasons. You have to put some reasons inside, reasonable answers and unreasonable.
So it has to be logical.
Yes.
All right.
Okay. So these are the sample space. What are the types of sample spaces? Types of sample spaces. So in general, sample spaces can be discrete or continuous. What's the difference? Continuous sample spaces.
Like a dice. 1, 2, 3, 4, 5, 6.
Is that continuous?
No, that's discrete.
That's discrete. Let's try to understand what's the difference, and then you will find it easy to differentiate. Continuous sample spaces consist of intervals of real numbers, or the whole real line, and generally has to do with things that are measured. So for the things that are measured, like depth, temperature, pressure, height, weight, all of these are things that you measure. And this will always give rise to a continuous random space. So the sample space is part of the real line. It's the whole real line or part of the real line. Continuous sample space. However, discrete sample space has to do with the integers, yani whole line or part of it, of the integer or whole set. Let's say not line. And has to do with things that are counted, not measured. So whenever we talk about an experiment to count things, we'll have a discrete sample space. Number of tosses, number of tries, number of calls, number of text messages. We can count those. However, we cannot count the temperature. We don't count the depth. We don't count the humidity or the temperature. So things that are measured will result in a continuous sample space, while things that are counted will result in discrete sample space. Right. Then discrete sample spaces are two kinds also. So discrete sample spaces are two parts, what we call finite. They can be finite or countably infinite. So what does that mean? What's finite first? I think finite is
a limited number.
Limited number. So you can, if your sample space, you can count all the, for example, tossing a coin, head and tail, two of them. It's limited number. Or throwing a dice, I have 1, 2, 3, 4, 5, 6. It's finite number. So finite means limited number of outcomes in S, in the sample space. You have limited number. Countably infinite, then it's unlimited number of outcomes sample space, like this one, right? So an example of unlimited number in discrete sample space, example, number of tries to get ahead. Sorry, number of tries to get ahead. Why do we call it countably infinite? So here the number is infinite, but why do you think we call it countably infinite?
Because it's integers.
Because they are integers. So what? You're right, but I need more explanation. Why? For example, the depth. Let me say this: the depth example. We said how many possibilities we have for the depth? Infinite possibilities, right? For the depth, we have infinite possibilities. How many numbers I have between 2 meters and 15 meters? How many numbers I have on the real line between 2 and 15? Infinite, right? And here, how many numbers I have in this S? It's also infinite. So what's the difference?
Doctor, here they are all integers. They are just integers.
Okay. Yeah, I see that you probably yeah. Can you mute your mics? I see it's probably you. I think you understand it, but you need to express it in a slightly better way. Saying that it's integer, yes, we can count integers. So countably infinite. This is the way, at least I look at it. Means if you take a slice from S, then you can count the number of outcomes inside it. Let's see. So for S, that is 1, 2, 3, 4, 5, all the way to infinity. The sample space that we talked about. If I take a slice, how many I have? 3 outcomes, right? I can count how many outcomes inside a piece of the sample space. However, if my sample space for the continuous example, it's the real line between whatever we said, 2 meters or 3 meters. Abdullah, 1 second, Abdullah. I will finish this and then get back to you. Between 1 and 15. 1 meter and 15 meter. This was my sample space for the depth example. So now, if I slice it, let's say between 5 and 7, then how many I have here? How many points I have between 5 and 7? Can I count them?
No.
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 It depends about how many decimals you're gonna use, I think.
No, you
But
can.
there are infinite possibilities.
And yes, between any piece on the real line, it has infinite number of outcomes. So this is, they are both infinite, but this is countable, and this is uncountable. They are both infinite, but one countable, one uncountable. Abdullah, go ahead. You have a question?
Yeah, Doctor, I get confused about the S notation. Does it represent the number of possibilities or the possible outcomes? You get my question?
No, because I think you repeated the same meaning in different way.
Okay, I'll try to make it better. Now, for example, for the coin, you said there are infinite possibilities to get head or tail.
No.
But above,
no. You have to be careful about what experiment we are talking about. The experiment I'm talking about here is keep tossing the coin until you get a head. It's not one tossing. You keep tossing until you get a head. So what are the possible outcomes? In this case, possible outcomes are 1, 2, 3, 4, 5, all the way to infinity. Right?
Okay.
And for the C, is just taking measuring the depth. So in both cases, you will have infinite outcomes. However, for the continuous one, it's uncountable, while for the discrete one is countable. Okay. So let's do the next definition. Probably before doing the next definition, I will take the absence. Let me. Okay. So next we will define. So we defined sample space, and then next definition is an event. I think we are moving a bit slow. This, but okay. I'm just logging into my Blackboard. So you are L02. Okay, I will go to attendance and I will start the checking in. And you need to check in. You will not get any pin. Last time we had, I guess, or not, I don't remember if it was this group or the other group. We had students who did not check in. Make sure you have 2 minutes to check in your attendance. So go to Blackboard and check in your attendance, and then we'll continue the class. Please, all of you, go to Blackboard and check in so that you are counted, not absent. Yes, Sultan.
Doctor, I have a question about the S symbol.
What was the question?
Is the S the number of outcomes, or does it depend on the experiment?
S is the collection, is the set. S is a set that contains all the possible outcomes. So different experiments will have different S's.
Oh, okay, thank you.
Sure.
Doctor, last
Yes.
Monday I was in the lecture, but in the Blackboard lecture, not this one. I was attend, but you mark me as an absent.
I will not, the first lecture, I will not count the absence. Don't worry. So make sure you check in today.
Yeah, I already checked in. Thank you, Doctor.
Okay, sure. Okay, we have 30 more seconds for people to check in. Make sure you check in before it's over.
الو دكتور.
Yes.
دكتور انا الكونكشن بس صار عندي فيه مشكله، يعني فاتح من على الموبايل فما عملت تشيك ان لسه.
خلص التشيك ان
وسكر
راحت
علي
عليك.
على البلاك بورد. فيك تفتح لي بس دقيقه؟
ما بعرف والله شلون يفتحوا يعني.
طيب ايش اعمل مشان الحضور؟
صير احضر من الكمبيوتر مو من الموبايل.
بعرف والله دكتور،
Next
بس
time.
لانه انا كنت بالشغل جوا الجامعه وكنت راجع على الطريق.
ما شاء الله. Just send an email to Sujoy and copy me. That
طيب
you
ابعث
could
لك
not
ايميل
check in.
دكتور؟
أنا وسجوي TA.
تمام.
Okay.
تمام.
Okay.
بالعافية.
So let's define the event, and the event is simply an event is a subset of the sample space. Very simply. So if we have the sample space like this, and it has certain outcomes, we can put them as dots inside the sample space. Then I can have different outcomes, different events. I can have this as event 1. I can have this as event 2. I can have this as event 3, and so on. So let's give some examples of events. Like in throwing a dice, we said S is 1, 2, 3, 4, 5, 6. So based on that, you can define some events. You can define E1 event of getting an even number. So you are interested only in the case of getting an even number. So what's E1? E1 will be part of S, which is 2, 4, and 6, right? Somebody else might define a new event, which is getting a number less than 4. So E2 in this case is 1, 2, and 3. So, and you can visualize this again using Venn, what we call Venn diagram. So if this is my S, so here I have how many outcomes? I have 6 outcomes. I will draw them like this. 5, 4. So what's E1? E1 is the E. And then what's E2? E2 is the number less than 4. Then this is E2. And we can move to defining what we call events, operations, or combinations. So we can have union of events. So E1 union E2, which is all outcomes in E1 or E2. So in the above example, what's E1? Union E2. I have everything except the 5, right? So 1, 2, 3, 4, and 6. You still hear me, right? I'm not sure because
Yes, doctor.
Yes, doctor.
Okay,
Yes,
because
doctor.
I'm muted. I had someone came in, so I'm muted for a second. Okay, so this is the union. We can also have intersection of event. I'm sure this type of things you have seen before. So this is just going over it again. Intersection of events. So E1 intersect E2. It's all outcomes in E1 and E2 at the same time. So in this case, E1 intersect E2 will be what? What's the intersection of E1 and E2? It's just number 2, right? And we can have the complement of events. Which is, for example, E1 prime, which means all outcomes in S that are not in E1. So the complement, everything outside an event E1, and in this case, what's E1 prime? So E1 was E1 the event of 2, 4, 6. So E1 prime is the odd numbers, which are 1, 1, 3, and 5. We can have what we call mutually exclusive events, or sometimes called disjoint events, which is the case when E1 and E2 have no outcomes in common. So if EI intersects EJ equals phi, which is the empty set, then EI and EJ are, we call them mutually exclusive. So what's an example of mutually exclusive event? So if I have E1 as the even number, E3 as the odd numbers, then those two are mutually exclusive. They do not have any outcome in common. So as we will see later, Abdullah, go ahead.
Doctor, what kind of events we can use this diagram for?
Venn diagram?
Yes.
يعني mostly it's used with finite, discrete sample spaces. Otherwise, you will not be able to do it.
Okay, thank you.
Okay. So, as we will see later in the course, mutually exclusive, there is a difference between events that are independent from each other and events that are disjoint or mutually exclusive, and these are not equivalent. But we'll talk about this later. I don't want to waste time now on this. But let's what I started. Let's continue with representing is using Venn diagram. So we can do all the operations that we talked about. So if this is my S, this is E1, and this is E2 in general, then in general I have outcomes all over the place. Then if I am interested in E1 intersects E2, then we are talking about outcomes that are in the common area between E1 and E2. If we are interested in again, if we are interested in E1 union E2, then we want to cover all the area that is either in E1 or in E2, and in this case, we will count all the outcomes that are inside any of them. Similarly, we can do the complement. So if I have, this is E1, and you are interested in the E1 prime, so we are talking about all the area outside, all parts of S that are outside. So in this case, we'll have all the event outside. Of course, E1 will have some events inside it, but it will not be part of E1 prime. And finally, we can have disjoint events or mutually exclusive events. So each one has its own outcomes, and then I might have some other outcomes outside. And here I have E1 intersects E2 is just the phi or the empty set. We can also talk about more set theory rules. which, for example, we have the commutative law assembly, which is very straightforward. If we have A intersects B, then this is equivalent to B intersects A, or A union B is the same as B union A. So this is what we call the commutative law. Also, we have the distributive law. So distributive law, if you have A intersects B, A union B intersects C, then you need to distribute C on A and B. So you can look at this as A intersects C, and then this is union B intersects C. So you can take this inside and intersect it with each one, and then take the union of the result. And you can do this also for if you have A intersects B union C, then you can distribute this inside so that it's A union C, and then intersects B union C. Also, we can have the associative law. These all are straightforward rules. So in this case, if you have A union B union C, this is the same as if you take the union of B and C and then you do it with A after that, and the same for A intersects B intersects C, then this is the same as A intersects B intersect C. So all these are some straightforward events. The last one is De Morgan's law, what we call De Morgan's law. And De Morgan's law is simply when you complement, if you have A union B and you want to take the complement for the whole set of A union B, then you take the complement of each one and then you flip the operation in between. So if you take this inside, then you put it on A and B, and then you flip the operation inside. Let's see, using Venn diagram, is those two sides of the equation are the same or not. So let's plot A union B complement. So we can use Venn diagram to prove such relations. So if this is my A and this is my B, so now what's A union B? A union B is this, right? What's the complement of that, which is what we are interested in red? So the complement of that is everything outside it. So in red, I have A union B complement. So let's see if I plot the right side. Is it the same or not? So let's see. So again, this is A and this is B. So let's see what's I will use the color codes. So I will put A bar in this color. So what's A bar? A bar is everything outside A. This is A bar. What's B bar? Let's do it in green. I will do B bar in green. B bar is everything outside B, right? So everything outside B is B bar. And now, what's the intersection between A bar and B bar? I will write it in, I will do it in red. So A bar intersect B bar. What area in this graph that has both blue and yellow?
Everything outside A.
Outside them both.
Outside them both, right? Which is the same as the one on the left. So De Morgan's rule, if you are complementing a set that is a union of two events, then you complement each individual event and then flip the one in between. The same as if you have A intersects B, prime, then using the same logic, and you can prove this yourself. So this is A bar union B bar. You just flip the one of the in the middle. Finally, what's the complement of the complement? So meaning that if I have prime, A prime, prime, what would that give me?
A.
That will give you A, right? It will give you A because two primes will cancel. So we'll cancel each other. Okay. Good. With this, we finish what we want to say about the set theory, and we are ready to move to the third topic we want to talk about today, which is the counting techniques, which is a very important and interesting topic. And this topic, for those of you who later on will go for graduate studies in big universities who ask for GRE exams, at least at the time I took GRE more than 20 years ago, probably 25 years ago, counting techniques were the main part of one of the sections, I guess the quantitative section of GRE. I'm not sure about the structure of GRE right now, but these are very interesting from all aspects, from the course and otherwise. So under counting techniques, we'll be studying 3 different rules that you can apply them in different scenarios based on what scenario you want to work on. We'll talk about the multiplication rule, then we'll do permutations, and finally we'll do combinations. And here we will look into some very interesting problems that the problem probably we'll do next time about chances of having 2 of you in a class of 39. We'll calculate the probability, and we can see later on if it applies to you or not. The probability that 2 of you have the same birthday, and having 38 students, we have a good chance that 2 of you have the same birthday, by the way. But we'll see how to calculate it, how to find the exact probability of having this event. Okay, so let's start with multiplication rule. And where do we use it? Simply, we use multiplication rule if we have an operation that consists of k steps where I have n1 ways to do step 1 and 2 ways to do step 2 all the way in k steps to do step k. Then the rule says the total number of ways to finish the operation, total number of different ways to finish the operation is n1 times n2 times n3 all the way to nk. So what does this mean? Let's do an example. I think the best way is to do an example. Very simple example is when you example 1, simply you go to a fast food place, and then you will you want to pick a drink and a sandwich. Let's very simply, it's like you will pick first the drink. So in the drink you can get Coke or whatever, 7-Up, and then a sandwich, let's say burger, chicken, whatever, or wrap. Yes. So how many different alternatives for the drink? You have 2. How many different sandwiches you can pick? 3. Then total number of different meals is 2 times 3, which is 6. So you can have Coke with a burger, Coke with a chicken, Coke with a wrap, or 7-Up with a burger, 7-Up with chicken, or 7-Up with a wrap. Or the example that I always give to my students, which is about travel. So not sure if you like to travel. I like to travel, and we were trapped for a year now. If I want to go from Doha to Chicago through London, I know now Qatar Airways goes to Chicago directly, but personally I don't like long flights, so I like to get in the middle, get some rest, have some food, and then continue. So how many different ways you can go from Doha to Chicago through London? So we can go from Doha to London. I'm not sure if some of you like to travel. So how many different airlines that go directly from Doha to London? What options do we have? Qatar Airways for sure. Turkish?
I think British.
British Airways. Turkish, you can go anywhere, of course. I'm talking about direct flight. Of course, you can use, if we're not talking about direct flight between the 2 points, then...
American flight.
From Doha to London, no, just Qatar Airways and British Airways. But now from London to Chicago, we can have again British, right? British Airways. We can do American Airlines. PAM America. What's PAM? I don't know what's PAM. I know there used to be an airline called Pan America. PAM. I don't know. So I know United Airlines, Delta Airlines, yes. Continental, I guess. And the Virgin Atlantic. Let's see. So let's say these are the possible different ways to go from Doha to London. Then I have here 2. I have here 2, 6. Then 2 times 6 equals 12 different ways to go to Chicago.
Doctor, this is similar to permutations and combinations, right?
We'll see. Next time we'll do permutations and we'll see how is that different. But we'll do next time. I don't think we have time to get into permutations and combinations now. But what's related here is someone might say, why don't we just add them? And so, or when do we add them? Why don't we just add them? So when is the way, like for this is more easy to look at? Why don't we add? We just add them. So let's do a quick example. For example, if you go to a fast food, so if you go to a fast food, for example, I'm not promoting fast food; it's not healthy, but and you want 1 sandwich, and the options are, for example, burger with cheese or without cheese, chicken with or without cheese, or wrap, for example, with or without cheese. And you are looking for 1 sandwich. How many different ways, how many different sandwiches you can get? We have 2 options here, 2 options here, 2 options here. So how many total different options that you can get a sandwich? In this case is 2 plus 2 plus 2, which is 6. Why didn't we multiply them? Because here, this is not a process that you are doing it in steps. This is 1 step only, but you have different options for the same step. It's like how many ways you can go from London to Chicago, or how many ways you can go. You are picking only one sandwich. If we are picking 2 sandwiches, now you cannot do it. 2 out of 3 options. We'll use permutation and combinations, as we will see next time. But simply, the multiplication rule has to do with any operation that you do in steps, and you want to complete the whole operation from step 1, step 2, all the way to step K. So we just multiply the options at each step to get the overall number of routes or alternatives that we can get out of this experiment. Okay, with that, I will stop at this point, and if you do not have any question, please, you can leave. If you have questions, I can stay around to answer your questions. Otherwise, feel free to leave. Thank you, and have a good day.
Thank you very much, Doctor.
Thank you.